Welcome back. Up next, we'll hear from Professor Dr. Tim Kacprowski, Director of the Institute of Data Science in Biomedicine at Technische Universität Braunschweig. His research merges systems medicine, network biology, and AI to understand the molecular foundations of complex diseases. Today, he'll guide us into one of the most crucial challenges in AI for medicine: interpretability and robustness. These are questions that determine whether AI can truly be trusted in clinical practice. Please welcome Professor Dr. Tim Kacprowski.
Thank you, and welcome back. So, in the introduction of the opening of the summer school, people already mentioned things like fairness and so on in AI, which is arguably probably the most important aspect of this if you go into medical applications. But since I submitted this title way before the opening ceremony, I apologize that I'm not talking about fairness now, but I'm rather talking about interpretability and robustness, which are kind of the basics to bring us to fairness in AI eventually. So I hope this fits nevertheless. And I hope I'm also telling you something new and something useful for the cases where you are going to build your own AI systems, no matter if it is a random forest, a support vector machine, a language model, what have you. All of this at some point deals with and should be based in some interpretability and robustness. So we'll cover some basics, things like what you definitely should do, and surprisingly many people still are not doing when they publish machine learning stuff or artificial intelligence stuff, namely cross-validation and permutation tests. And then we'll go through some examples for techniques regarding interpretability of what your model is doing. And we'll mention some things regarding investigating the robustness of your models. So starting with the basics. I don't know if you're familiar with XKCD or if you've seen that comic before, but you hopefully are not some of the people, and you won't be those people, but there are people out there who, listen to AI lectures, for instance, like Thomas just gave one, or go to the internet, do some machine learning course. Then they run onto Kaggle and they find an interesting problem, and then they do an AI, and then they're happy that they did something, but nobody knows why it actually works and what it's doing, right? And to give you a more concrete example, back in the days, we were looking at ultrasound measurements for liver diseases. You can use ultrasound to measure things like liver stiffness. And the physicians of you probably know, if you're stand on a stage and peek your own liver and then you realize, oh, this feels hard, then it's time to leave the stage and see a doctor, right? If this is still like squishy and your finger somewhere gets lost in your belly, then everything's fine and you can keep on talking. You can quantify this by using ultrasound imaging. Now, people figured this out and they developed a machine learning model that uses ultrasound measurements to predict a liver disease. This worked so well that the company producing the ultrasound machine said, hey, this is cool. We just have a one-button solution. This is like the thing every clinician wants, right? You scan the patient on the machine, you press the button, the machine says, this patient is healthy, or this patient has a liver problem. Turns out, this works very well exactly on those people where people developed the model. Cohort in our hospital, and it didn't work at all. Now you can say, okay, but there seems to be some information in there, so let's just retrain the model, make it more robust, and then it'll work for us as well. Now, here's the crux of the matter. This company was so fond of this machine that you do not get the raw readout of that machine anymore. You only get the score out of that. So the data that you need to retrain the model is not accessible anymore. And this is stuff that happens if you go out there and design an AI without taking care that it's robust and that it's interpretable. And that is stuff we do not want to happen, right? which is why we're going to talk about this. So the first thing you should do is something called cross-validation. Who of you has already heard about cross-validation? Just quick show of hands, maybe. Okay, so there still are people who have not heard about cross-validation. Then let's briefly go through this. So if you train a machine learning model, you've seen before that you have some kind of loss function or some error measure, right? Where you say, okay, now my model made a mistake when predicting something, or my model was right in predicting something. But you have different kinds of errors. You have a so-called training error, which is the error you make on your training data. But you also have a test error, which is the error you make on data that your model has not seen before. So this is arguably the more interesting error, because this is the one your model will make when people are using it. The training error is something that only you see while you develop the model, right? But the test error is really something that you want to avoid. And surprisingly often, the training error can dramatically underestimate the test error. So the error your model will make in the real world once it's deployed is usually much larger than the error it makes during training. Any idea why that's the case?
I think that it's sorry. The error becomes for something called overfitting. Overfitting, I think, means that the model knows very well the data that it's training with. So when the model sees another data that has never seen before, the model can struggle a lot predicting what you want to predict. So I think that's the case.
Yeah, exactly. So in the very extreme case, that's overfitting, because your model tries to perform very well on your training data, and your model cannot try to perform well on the test data because that's data your model hasn't seen or doesn't see, right? So we need to find a way around this. And this goes back to this bias variance trade-off that you have in machine learning. When you want to visualize this, let's say we just want to learn some kind of regression model fitting this data here, then we can just plot a line which arguably doesn't fit that data very well. So that would be called underfitting, because our model could perform better for that data set. If we, let's say, train too long or have too many variables in a model, right, we might see something like this, which is the overfitting that has just been mentioned, where your model really perfectly tries to fit and predict every single data point that you have. What we want is rather something like this, right, where you kind of can generalize the shape of your data, if you want, without sticking to every little detailed individual data point. And the question is, of course, how to get there. You can see this for various models. So for regression models, it could look like this. You can also see this in classification models, right? So here you would have the underfitting case. This would be the ideal case. And if you see something like this, this could be considered overfitting of your classification. And if you work with deep neural networks, people typically look at this error or loss function in terms of training and validation. And what you want to see is something like this. So if your validation error is very close to your training error, then you're usually underfitting, which means you can improve your model still. If you see something like this, that at some point your validation error will increase again, this is a clear indication of overfitting. And you want some difference between these errors here without the validation error exploding again. So these are kind of some, if you want, diagnostic plots on a very simple level that you can look at if you have developed your model to check whether you're underfitting, overfitting, or if you did everything correctly. Now, how to avoid this? Most of the time, you're just given a data set and you're supposed to develop your model. And it's usually very hard to collect more data, especially in medical contexts, right? Ideally, if you want to look, let's say, for biomarkers or some kind of therapeutic indications, many diseases actually happen in tissue. So ideally, you want tissue samples to learn something on, right? And it's not so easy to collect, let's say, brain tissue samples, right? You cannot just say, hey, I'm a fancy data scientist. I want to improve my model. I need more data. So can you give me a piece of your brain? That's not going to happen, right? So you have to somehow work with the data that there is. One way to do this is this holdout method, where you just divide your data in two parts, and then you use one part, usually the larger chunk of the data for training, and a smaller chunk for testing. The important thing is that you are really not allowed at all to look at this test data. You can only use the training data, and only once you say, okay, I'm happy with my model, I assume this model is perfect, or at least as good as I can get it, then you can test your model on the test data, not before, right? And there's, of course, a bunch of questions associated with this, like how much data do I need in my training? How much data do I need in my test set? Also, you're still kind of limited to what you see in the test data, and you cannot generalize your prediction error outside of this test data set. So there's still some kind of overfitting depending on how much data you have and how the distribution of your samples and features looks in this piece of data that you have, right? And this one single training set or test set doesn't really tell us something, or might actually tell us more than we want to about this specific data set, and nothing about what happens if we have a distribution shift. For instance, if your data set comes from a hospital in Mexico, your performance might be very different if your data suddenly comes from a hospital in Germany, because Germans drink more beer, or I don't know, right? Whatever the reason, the data will look different than the one you trained with. And then there's many fancy models that have things called hyperparameters. So it's not always the case that you just do your standard linear or logistic regression where you fit your estimates and then you're happy. But you might have things like, let's say, a random forest, where you need to determine the number of trees that you want to use, the depth of the trees that you want to use. So you have kind of screws that you can adjust on which the performance of your model depends, right? Those we call hyperparameters, and those have to be tuned for your model to work well. If you do that, you're missing one data set if you only have training and test data, because you need a separate data set to optimize these hyperparameters for your model to work well. You need the training data to see if you can fit the model with the current hyperparameters. Then you need kind of a validation data set to tweak the parameters a bit and see how the performance changes and to find the best set of hyperparameters. And you still need the test set to assess the generalization performance of your model, right? So if we go with the holdout method, then we already need to divide this data set in 3. And I don't know how many people of you have ever tried to build, let's say, real AI models with real clinical data. If you do, you know you will not have enough data to split your data set in 3 parts and still do something meaningful with that, right? I mean, we, as data scientists, we go around and tell biologists, if you want to do a t-test, you need 3 samples. And then the biologists tell us, but I only have 2, so what do I do? Well, certainly no machine learning, right? So it might look trivial, but it's actually hard to find a data set that you can split in 3 data sets that are still large enough to do something meaningful with that. Of course, if it goes down to 2 samples, we're in an extreme case where you cannot do anything anymore and you just go home and have your coffee and, you know, find a more interesting problem to solve. But if you just don't have enough data to do all this holdout stuff, then you can try what's called cross-validation. Again, the goal is to estimate your generalization error. You want to avoid the sensitivity to your training or test set, and you want to use as much data as possible. How can we do that? We can use every bit of data for training and for testing, just not at the same time. That's kind of the key idea behind this cross-validation mechanism, right? So you divide your data in k blocks, Usually k is 3, 5, or 10, or if your favorite number is 42, then you can do a 42-fold cross-validation, where you do then k runs of model training, and you always use k minus 1 parts of your data for training, and the kth part of your data is testing. And you can do that k times. And then you can just average the whole thing, because we're doing statistics, and all we do in statistics is basically averaging things. And then you have your final validation. The beauty of this is that those k runs are independent, so when you test your model on fold k, you can train it on fold 1 to k minus 1, and it will not have seen fold number k, right? So all this idea of testing the model on data that it has not seen still holds. Albeit, of course, you use all of these folds in k minus 1 folds also as training, which means you still risk some overfitting, and you still will have a hard time tuning your hyperparameters. So we're already one step further in what we can do with little data, but it's still not the optimal setting. Mind you, the optimal setting is only you get out there and get more data, which is unfortunately also the least realistic setting. We can do this to the extreme when we do something called leave one out cross-validation, where k, so the number of folds you do, is basically the number of samples you have. Meaning that you will use all of your data except one sample for training and this one sample for testing. And you can do this k times with hopefully little overlap and data leakage between your training and your testing data. One thing you should take care of if you do this cross-validation, because you can already get feature drifts into your cross-validation if you're not careful, is that you should stratify this. So let's say you have male and female patients, for instance, and it just so happens that you will find one split of your data where your training set consists only of male patients and your testing set consists only of female patients. Then you will have a feature drift between from your training to your test data. And that is something we want to avoid. So you use stratified cross-validation, where you try to keep this balance of female and male, or wolf and dog, or whatever it is that you have, the same in all splits of your data. Now, arguably, this doesn't work for leave one out cross-validation because we only have one sample, right? But for k-fold cross-validation, this is the way to go. So how can you check if you actually did a proper cross-validation? So you have to make sure that your held out test data is really representative of something that's going on out there, right? So you want your test data to look like you expect data to look that your model will use once it's released, let's say. And you have to take care that your entire processing and model fitting procedure separates those data. So just as a quick check, we have some data set and we want to find the 20 best features that show some strong correlation to our outcome. Let's say we want to predict if a patient will die within the next 2 years or not. And then we check which features have a high correlation to death within the next 2 years. And then we use these 20 features to build some classifier, and we estimate the prediction error of the model using cross-validation. Is this a correct strategy? Who thinks yes? Show of hands. Who thinks no? Show of hands. Who has no clue what I'm talking about? Show of hands. Okay, fair enough. Well, it is not, right? Because when we find those 20 best features that show this correlation, we're using the whole data set. So we have already looked at the whole data set before we even start building the model. And you might remember about the holdout method I told you. You really absolutely must not look at your test data at all before you're not 100% confident that this is the best model you can do, and then you test it, right? So to find those 20 features here, looking at the whole data set is way, 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 way too early. So you need to split your data before you even start doing that for this to become kind of a valid cross-validation procedure. Let's look at a similar problem. We start by dividing our data set into k subsets. So nice, we already learned something, and just divide the data right at the beginning. Then for each subset, we find the 20 features that correlate, and then using those features, we train a classifier. And then we use the kth data set to estimate the prediction. So this sounds a lot like the cross-validation, right? So would this be a correct strategy? Who thinks yes? Who thinks no? Who still doesn't have a clue what I'm talking about? Okay, at least that number is down to 0. Nice. But the yays had it, and that's unfortunately almost right. It depends on the model you use. So this goes back to the hyperparameter tuning, right? If you use a model that has hyperparameters, then you need to tune those in another round of cross-validation. Because this is only one round of cross-validation, and it only gets you so far. If you do a regression or one decision tree or something like this, then this is fine. If you're moving into random forests, support vector machines, or anything with some parameter, then this is still not enough. Then you need to do something that looks as awful as this. So what we're doing is basically we have a data set, we split it in two. We have our test data set and our training data set. And then our training data set is again split in two, and then we have some inner cross-validation here. We use the results of this, ideally weighted according to the performance of our model, in some outer cross-validation, and then at the end, we have a properly cross-validated model, hopefully. All right. Now that you all know how to properly cross-validate your models, and by the way, I don't know how the logistics are planned. I don't think you need to take pictures of the slides. You will probably have access to the slides later, right? If not, just give me your email address and I can email those slides to you. Anyways, now that you have cross-validated your model and you're confident that your model performs well out there in the real world, let's look at permutation tests, because the next question is, what has your model actually learned, and has it learned something meaningful? So what is the probability that whatever you found as a connection between training data and or between your data set, the features, and your outcome really means something versus it's only chance, right? You might be familiar with that concept. Sounds a lot like a p-value from statistical testing or something. And this is basically exactly what's going on. And these permutation tests are kind of a multiple testing correction for machine learning, if you want, right? You try to create a scenario where your features have nothing to do with what you want to predict and check if your model still works. And if it does, boy, you should go home and try again. If you destroy any connection between your features and what you want to predict, then your model should not work anymore because there's nothing that it can predict, right? Now, here's the shocking news. If you go out there and look at machine learning models that you find on PubMed, on wherever, most of them still work if you do that. Because people don't do these kind of tests. And this also allows you to do something else, because whenever people try to develop a new machine learning model or a new AI, of course, they want it to be better than everything that's out there, right? Same for us. If we want to develop a new method, we want this method to be better than the methods that are out there, which we tried with something called TRIPS. Doesn't really matter what it is. It's an AI model that predicts something. And we compared it to other methods out there, which are called RegEnrich, Cactus, and PCSF. Again, doesn't matter what they do. It's machine learning that predicts something. And we saw that our new method doesn't really perform as well as the best method that's already out there. And then we were really disappointed. But if you do permutation tests, you will actually see that here from left to right, we kind of perturb the data and destroy all the correlations that we see more and more, right? So the further right you are in this plot, the less connection there is between your features and what you actually want to predict. And if you look at RegEnrich here, it doesn't really care, at least until this point here, right? At some point, performance goes down. But if you look very closely, you see that with randomized data to some degree, it even predicts better than with real data. This is not right. This shouldn't be the case, right? Whereas with our method, we see that it actually degrades in performance, at least to some degree, if we do these permutation tests, right? And so this can still give you an argument that while if you look at those standard measurements like AUC and specificity and what have you, your model might not be the best. You might still discover that your model is actually more meaningful than the other models out there. So permutation tests are not only something annoying that you have to do to make sure that your machine learning works, it's also something that gives you a way to show that your machine learning actually does something meaningful compared to what other people do. So this is basically how it works, right? So you shuffle your data, either the features or the class labels or whatever. It doesn't really matter if you do it on the feature side or on the class label side. Then you train your classifier again with your permuted labels. You compute some performance measure, whatever performance measure you like best. And you do this many times to get what we call a null distribution. So you get kind of a distribution of how well your model performs on random data. And you compare this to how your model performs on real data. And if you do this and then you see something like this, where the blue boxes are basically performance on random data and the red dots are the performance on your real data. On the y-axis, you have the error of your model, so you want the error to be low. Who thinks that this is a meaningful model? Who thinks it's not a meaningful model? And who just raised their hand because the guy who gets everything right raised their hand before you? Okay. But then you actually already learned something, right? Because this is a very badly performing model. Because the performance on the real data is not really better. I mean, sometimes slightly, but it's not convincingly better than the performance on random data. So the way this plot should look, if your model actually learns something meaningful, is that all those red dots should be down here or even further down, right? Not within the vicinity of those blue boxes. And this is something you should definitely always do whenever you train any machine learning model. Please. So now we covered the basics and we know how to actually assess how our how well our model works and to see if it actually learns something meaningful. How can we interpret what the heck this machine actually did? How did it reach the decision? Why does it tell us whatever the heck it's telling us? And there's two kind of very closely related concepts. One is interpretability and the other is explainability. Now, interpretability usually focuses on understanding the model. So how was the decision reached? What did the model do? And explainability usually justifies the decision. So why does the model tell us that we need to treat this patient first? Now in this lecture, I will just intermingle these two terms because it's just, for all practical purposes, you can treat them as synonyms, unless you're into hardcore machine learning theory and whatnot, but I assume none of you is. Okay, then this just means the same for us. Right? We want to understand how the model works and why it reached a certain decision. We usually want to know this, but it's not always necessary, right? So if you go to, I don't know, Amazon or Spotify or whatever, and you have these kind of recommendations, then who cares why the model thinks that you should listen to this song next? It's either right or it's not, right? But who cares why? Also, if you're, I don't know if social media these days still recommends friends. Back in the day when it was hip for me, you always had these suggestions of, hey, here might be some friends for you. And then turned out most of the people were actually boring and, you know, I just wasn't good these days. And also in robotics, who cares why a robot works and why it does whatever it's doing, right? Sorry for the robotics guys in the room, but explainability is usually something that we don't need in robotics. You still need to understand how the robot should behave, though. To give you an example, if you design robots for humans, you want to avoid collisions between the robot and the human, right? That's kind of intuitive. You don't want the robot at the assembly line hitting one of your workers while trying to assemble a car or whatever. But If you design robots for cows, this becomes a very different story. You know how cow hierarchies work in cow herds? Well, the cow at the top of the hierarchy is the one that bumps all the others out of the way, right? And if you design a robot that's supposed to deliver food to the cows, and you let it run around in a cow barn, and this robot kind of tries to avoid collision with the cow, what will happen is that at some point this robot will be at the bottom of the hierarchy, and will just be confined to a very small corner in the barn and not be able to deliver the food anymore. So instead, if you design robots for cows, you want that robot to push the cows out of the way to make it clear, hey, I am the boss here, right? Otherwise you will not have any food. So even though you don't need explainability, you need to be aware of the surroundings and kind of need a meaningful way to analyze what the robot is supposed to do or not to do. However, we're into medical decisions, and obviously we need interpretability for medical decisions. We also need it for legal reasons. We have something called the GDPR, where everyone has the right to obtain an explanation of the decision reached. And I don't know if every one of you ever tried to actually contact one of these companies that collect and merge all your data and try to figure out why they reached the decision. It's a nightmare. And also for scientific discovery, we also need kind of interpretability and need to be able to understand what's actually going on and what the models do, right? So there are models who are nicely interpretable and kind of explained by themselves, things like regression, at least if you're not afraid of a formula to describe a line, then regression is rather simple. Decision trees are also still quite explainable, I would say, but how is it with a multivariate generalized linear mixed effect model? That's not that interpretable anymore, right? Or random forest. It's basically this collection of decision trees, but arguably much less explainable than a simple decision tree, if only because of all the randomization in there. And then we have black box models where you have no idea what's going on, like support vector machines or neural networks. I mean, you can, write down all the formulas and describe the math behind it, but that doesn't explain any decision of the model in a way that anybody can understand this without studying those machines for a couple of years. So what can we do? One approach is to try and crack this black box with so-called feature attribution, right? So which feature actually contributes how much to the decision of the model? And there are things like feature importance measures, which you have in random forest and so on, but those usually work globally. That is, they tell you how important the feature is across the whole data set that you have, not for an individual decision of your model. Feature attribution methods try to do exactly that. So for each individual sample or prediction of your model, they try to tell you how important was this and that feature in your data sets. And there's some properties that are desirable for these methods. One is it should work for any model, right? So if we have a method that can explain the decision of a support vector machine, we would very much like it to also explain the decision of a neural network. We don't want to come up with a completely new method just because we changed our machine learning model. The subset of features should be minimal. So if you feed in 200 features, there's no use in, or why 200? I mean, let's do some genetics and look at SNPs, and then you have 60 million SNPs. And you don't want 60 million SNPs to contribute something to your prediction, right? Nobody will be able to interpret that. You want a handful of SNPs that explain your predictions. And you want this so-called local fidelity, that this explanation works good for similar samples. That means if it works well for one old white male dude, it should work as well for the next old white male dude, right? So if the sample is similar, the explanation should also work similarly well for the next sample. Has anybody of you ever seen this problem, trying to distinguish wolves from huskies? So if you do, what comes next will not be too surprising, but if you haven't, if you look at this, we have the prediction of the model and we have the ground truth, and it looks rather good, right? We make barely any mistake in these predictions. But is that really enough? Well, We'll see. So we start with something called LIME, not as tasty as the fruit, but local interpretable model agnostic explanations. We'll try to get through this without too much mathematics. Let's see if that works. So the intuition is you have some data set and you learn some decision boundary of your model, right? So you can either predict that something is gray or that something is blue. And the decision surface looks like this. So if you have a new sample that falls here, you would say, okay, this is blue. If you have a new sample that falls in here, you would say, this is gray, right? As straightforward as that. Now, a way to explain this would be to just randomly sample data points in this space that we have here, and then put a weight to them according to how close they are to the sample that you're trying to explain. So you're trying to explain why the yellow dot is gray. That doesn't make sense. Why the sample that's indicated by the yellow dot here is supposed to be predicted as a gray class, right? And then you look at many data points close to this yellow point here in this space, and then you fit just a regression model, for instance, right? Which gives you like a line here, and then you can classify this that on this side it's gray, on this side it's blue. And all of this will be wrong, right? Because this will also be predicted as blue by the simple regression model, but we don't care because we only look at this yellow sample here. We want to know why this yellow sample is gray, and I should work with other things than those colors. And then this regression line here is just enough to explain, okay, this is clearly a gray sample. This goes back to something called Taylor expansions and Taylor polynomials, if you ever heard about those. If not, don't worry. What it means is that you can basically describe any shape of a curve. Let's say we have this black curve here with some straight line if you look closely enough or at a segment of that line that's small enough, right? So if we look only at this part of this black line here, we can nicely explain this with this, or fit this with this purple straight line, right? Obviously, this does not work if we look here, right? The purple line is nowhere close to this one, but it's close to this part of the black line. And so you can construct many straight lines, perpendicular, no, not perpendicular. What's the other term? Tangent, yes. To the black line, right, to describe exactly the shape of this black line. Now, this obviously depends on how large the segment of the black line is that you look at. If that segment is small enough, this works very well. As you can see in the purple line, if the segment gets larger, looking at the green or the yellow line, this does not really work well anymore. This is why this is a local approach, right? So you try to explain the predictions of a very complex curve like this with a very simple model like just a straight line, at least in a close neighborhood of the point that you're looking at. That's kind of the graphical intuition behind this. If we work through this of how we can actually do this with, let's say, images, then what you do is you kind of gray out parts of the image, so you only have some parts of the image. You do your prediction with a black box model, and then you have, I don't know, 85% confidence that this is a frog. When you see the whole frog, surprisingly, you only have 52% confidence for whatever reason. And if you see nothing of the frog, you have no confidence that this is a frog, right? So you do predictions based on randomly planked out parts of the images. You do this very often, and then you just throw this into one linear model. So this is just kind of, this is the line that you saw earlier, but now as an equation and not as a line. And then you just check what those coefficients here are for these parts of the images. And then you can say, okay, if we have a positive coefficient, then the presence of this part of the image, so this one here, for instance, does contribute a lot to the model thinking that it sees a frog. Is the idea clear? Somewhat. Okay. Getting back to the wolf and husky example, if we do this with this model, so we blank out parts of the images and check which part of the image was actually important to reach the decision, then we see what's important to classify this husky or wolf here is this part of the image, which has nothing left of the dog or wolf or whatever it is, right? And if you check this carefully with like all the examples in the beginning, what you will figure out is that this model does not distinguish huskies from wolf, but it detects if there's snow in the background of the image or not. Now, while this is funny with if you just do it with these kinds of wolf-husky pictures, there's other scenarios where things like this could be less funny, right? If you just learn something that you didn't want to learn. It also works for multi-class problems, actually, right? So if we have this image here, and you feed this into an image recognition pipeline, it can tell you that, hey, I see an electric guitar based on this part of the image, or I see acoustic guitar based on these parts of the image, or I see a dog based on this part of the image, right? So it also works for multi-class problems. And this is actually an example where it works nicely to explain these predictions. So this Lime approach can or is basically agnostic to the model that we use, so we can switch out either the black box model or the explanation. So we can do it with these straight lines. We can also do it with more complex or other explanatory models. The explanations can be made short. If you know anything about regression, you can plug in L1, L2 penalties and whatnot to shrink down the numbers of variables. The fidelity, so that is how true the model is to the actual prediction, like the prediction of your explanatory model and your real model, is actually easy to assess, and it's very easy to use. It's basically 2 lines of code if you actually want to do this. It is, however, sensitive to choice of neighborhood. The sampling ignores correlation between features. The explanations are actually quite unstable due to this sampling of other data points, so you might get 2 very different explanations if you run this 2 times. Because those random data points that you sample, so those black dots here, might be very different in the second one, right? And it only works for simple models. If your prediction model becomes too complex, it will be tough to explain the predictions by just drawing a straight line somewhere, right? So this is also a somewhat limiting factor, which is where those so-called Shapley additive explanations come into the game, and now, unfortunately, we need some mathematics. So Shapley values are from game theory, and the guy who came up with those actually got a Nobel Prize for this in economics. It's not as straightforward as drawing straight lines, but once you got the hang of it, it's actually really cool and a nice way to explain predictions. So they come from cooperative game theory, which means we kind of try to connect credit allocation to machine learning. That is, if you have a cooperative game with, I don't know, 5 players, and then there's a reward at the end of the game, how do you distribute the reward among the 5 players? And for some interpretation of fairness, it would be nice if the player who actually contributed most to the team winning would get the most credit, right? So if you have your group work assignments at university, wouldn't it be nice if only the person who actually did the work would pass the course and all others would fail? You know, at least to some interpretation of fairness, right? If you contribute more to winning the game, you will get more reward from whatever reward the game can hand out. And we can nicely calculate or tabulate this. Just as an example, if we have a game of 3 players, and at the end, the game gives you 900 points. You look at, okay, how do subsets of players perform in this game? If only one player plays this game, you only get 100 points, no matter if it's player A, B, or C. So it seems to be a hard game, right? One player is not enough. If 2 players play the game, well, if A and B play, they reach 700 points. If A and C play, they reach 500 points. And if B and C play, they also reach 500 points. If all 3 players play, they reach 900 points. So first thing, it seems to be rewarding to have more players in the game. And now you can just go through all possible combinations of players, but you have to look at the order, right? So let's say A and B want to play the game, and then C wants to join in. If A and B play the game, we know they get 700 points, right? So A alone would get 100 points. A and B together get 700 points. So 600 of those 700 points are due to B entering the game. You see that? Okay. Now, since we know that if 3 players play the game, they get 900 points. If we let C enter the game as well, C contributes another 200 points. So at the end, we will have 900 points. And you can do this for all possible orderings of players, right? So if C enters first, then A and C will have 500 points. So 400 points are due to C. And to reach the 900, if B enters as well, then B contributes another 400 points so that we get to the 900 points. If you do this for all so-called coalitions of players, you get these sums here and you can average them, and then you have kind of the average contribution of players to that cooperative game, okay? So if you were back in high school and choose your, I don't know, soccer team or something, you would probably choose A and B before C because they give you more reward in the game. So that's Shapley values. And they have some nice properties like efficiency, symmetry, dummy property, and additivity. You don't need to care too much about these formulas. But the point is that those Shapley values are the only values out there that satisfy these 4 properties. You can show this by looking at some mathematical axioms. So what this means is they're really cool. It's the only way you can satisfy these properties, okay? And those are nice properties in terms of game theory and in terms of fairness and so on and so forth. So that's something that you want, and Shapley values are the only way to get it. And we can use this now in machine learning when we interpret kind of the model performance as the payout in the game and the features as the players. And then we can use those Shapley values to measure how much a feature contributes to the decision of the model, particularly to a well-performing model. And if a feature contributes much to a well-performing model, it's better than if it contributes much to a worse-performing model. Is that connection clear? Somehow? Okay. In a linear model, this is all we need, right? That's trivial. I would probably say if I would give a math lecture. So you basically just have your feature and the expected prediction of your model, which is just the average of everything that you put into the model. And the difference between what you get out of the average and the actual prediction is the contribution of your features in the model, right? Now, just assume that this is nice and it's easy. Problem is, if we go into nonlinear model, or if we want this to be model agnostic, we have to face this, which is obviously not as nice, meaning it's computationally very intense to calculate this, right? So this is nice, this is ugly. If you want, just say the more exclamation marks you have in a formula, the uglier it is, because the harder it is to compute, basically. But we can look at this, and this looks a lot like this part here, right? So there is a way to actually make this work, which is this here. You don't need to care about what you actually do there, but point is you can make it work, but it's still growing exponentially with the number of features. That is, with each player you add to the game, this problem becomes harder. And with the next player you add, it becomes even harder. And with the next player, it becomes even harder. But the increment of how much harder it becomes also becomes larger with every player, right? So maybe if you add the 3rd player to a 2-player coalition, it's a bit harder. But if you add the 100th player to a 99-player coalition, you cannot solve this anymore. Now, the thing is, if you're into molecular data like I am, you usually have tens of thousands of players. So this is really hard. But you can solve this by a very similar way as we did with Lime, by just pretending that we have these things like feature is present or not present, right? So if we have age, weight, and color to predict something, we learn one model where age, weight, and color can join the game, and a second model where only age can join the game, but we don't let weight and color join the game. Not joining the game in this case means we just assign some random value here, right? Not the real value, it's just some random value. And if you do this, then you can actually formulate another linear model. This, again, as you see, has not a single exclamation mark, so this is nice. And then we can solve this, which is kind of a loss function, which gives us a mapping here. This h is basically what we do here, right? So either using the real value or just drawing a random value. This is what this h is telling us. This f is the actual prediction of the model. G is our explanatory model, and this pi thingy here is just like this huge table of all possible coalitions of players. And while you do not want to calculate this by hand anymore, it's still nicely solvable if you have a computer that's not too large, actually. The interesting thing about this is if you use this pi here, so kind of this tabulating of all these coalitions in the setting of Lime, then even Lime would give you Shapley values. So that means that suddenly Lime is everything that we want by just looking at those player coalitions. So by playing around with those, which feature do we use for what prediction? This is kind of the key idea behind those Shapley additive explanations. It could look then something like this if you actually do this, right? So you have a decision boundary, so you have blue and red points, and whenever the background is more red, then you predict that the point is red. When the background is more blue, you predict it's blue. And when it's white, you have no clue. So this works nice as a prediction, but what you get also out of those Shapley values is these kinds of plots as an explanation. So what does that mean? Well, you have a feature called CA. This blue here tells you that the value of the feature is low, so you have a low value for CA, whatever CA is. And since they're to the right here, that means the prediction of your model is increased. So it's more likely, let's say we want to predict who's sick, then with low values of CA, your patients are more likely sick. And your model predicts that your patients are sick because of low values of CA. Or if you have sex here, then if you have low sex, so usually you code sex as 1 and 2 or 0 and 1, right? So low sex would mean male, and high sex would mean female. That means your patients are more likely to be sick if they're male. So apparently we have some disease that we're looking at where there's some gender influence here. And these kinds of plots then help you to explain on a global level the predictions of your model. But you can get down with this also to a per sample level, right? So your average prediction of the model, assuming you have no information, no features whatsoever, would be here, this base value, so 0.54 or something. Your actual prediction is 0.67, and that is influenced by those features here. So everything you see in red kind of increases the prediction for this particular sample. Everything you see in blue decreases the prediction for this particular sample. And looking at these plots, you can get explanations, right? So which feature contributes how much to the actual prediction for that specific sample. So these Shapley values are more stable and theoretically better grounded than what we did with Lime. Again, the explanations can be made short and contrastive by looking at only a few features, right? Just by kind of limiting the number of players you allow to the game, basically. You don't have to go through any of this math stuff. You can just use the readily available implementations. So again, it's just 2 lines of code or something. However, you still struggle with correlations between the features, unfortunately. It's a bit harder to compute, right? You saw more exclamation marks in Shep than you saw in Lime. And sometimes the interpretation can be a bit tricky because you may end up in situations where those explanations actually contradict each other. But this is very rarely. You just need to kind of be aware that this might happen. Generalizing this, especially what we saw with the Wolf-Husky case for image analysis, what people do there a lot if they want to explain predictions is that they use these so-called saliency maps. They're an explainability technique for image processing, where the idea is basically that we use the pixels of the image as features, and at the end we draw kind of a heat map that shows us which pixels of the image actually were important for the model to reach a decision. So like in the Wolf-Husky case, we looked at all the pixels representing the snow in the background to figure out that this was actually driving the decision of the model. Yes? This is actually what we also did with the LIME technique. So you can use LIME to get saliency maps. However, in image analysis, people typically use all those deep neural networks and whatnot, right? Where those methods are usually not LIME anymore, because then you need to retrain the network too often, but you use kind of gradient-based techniques. Yeah, as it says here, right? Methods based on gradients, so backpropagation gives you kind of the gradients in a network, and then you can visualize those directly on a heat map, and this then gives you a saliency map. One small but conceptually maybe important difference is that we do in LIME is something that we do to the model, right? So we tell the model, forget this part of the image and tell me what you think now. Here we ask the model which parts did you use. So it's conceptually a bit different. But the result, what you get out of LIME, could also be interpreted as a saliency map. So those things typically look like this, right? So you have different methods to get these saliency maps, and whenever you see something red here, that means this was the part of the image that's actually important for the prediction. And you can already see that there's some techniques looking at only the gradient, for instance, is, well, arguably useful, because why would this look like a junco bird? I have no idea. Whereas here or here, for instance, this already seems like a much nicer explanation, right? So there's different techniques to get these maps, but there's something very important that you hopefully have already learned by now, back from the beginning of the lecture. Permutation tests. Is this meaningful? Turns out, many of these techniques give you the same explanation when you completely randomize your data. So that means this is not meaningful. Because why would random data be a junco bird? It's not, but the explanation is the very same as for the real junco bird, right? So even if you use these explanatory techniques, you have to be careful and have to keep these kind of permutation tests and so on and so forth in your mind. And one thing I just want to highlight briefly for those of you who are into deep neural networks and transformers and attention and whatnot is the Jacobian. The Jacobian is basically a matrix that gives you all partial derivatives in a neural network, and you can visualize this in a saliency map, and this gives you something that's very similar to the attention mechanisms that we find in transformers these days. So this is kind of an implicit attention that early neural networks already had before someone at Google said, hey, attention is all we need. Surprise, attention has already been around, just nobody saw it before or has called it attention, right? But this is a very nice technique to get these saliency maps, and it's something that's very akin to the attention mechanisms in transformers and so on and so forth. All you need to do is accept setting your target to your actual prediction or the actual prediction of the model. You use the activation of the last output layer in your network. And then you check the gradient not in response to the prediction of your model, but in response to the activation of specific neurons. And then you get this kind of implicit attention in these networks. If you're not into deep neural networks or attention mechanisms, you can just forget about this. But if you are, it's actually quite interesting. I actually have no idea how I am in terms of time. 10 minutes? Okay. So very quick robustness 101 in 10 minutes. Basically, the question is, how do we manage our models so that they adapt to changing data, right? So again, if we have trained a model on patients in Mexico and then we want to apply it to patients in Germany, how can we factor in all the beer drinking that happens in Germany? Or any other drift in features. One thing that you will see a lot, especially in medical data, is noise, right? So you have kind of random imperfections in data collection, which a robust model should not really care about. So for instance, if you have an AI diagnosing tumor from an X-ray, that should not be fooled if you have a more grainy image or a better resolved image, right? The AI should still be able to do a good prediction. What you can do is basically data augmentation. So you kind of artificially put noise on your training data so that the model sees noise in training and learns to cope with the noise already at that stage. You can also, if you have other data, you can remove outlier, you can use regularization techniques or so-called early stopping. So there's a bunch of things you can do to cope with noise in the data. And white noise is basically, if you have like Gaussian distributed noise, you can somehow see the connection that this white noise is basically the whole foundation of the theory of statistics and machine learning. So that's something we really shouldn't care about. In theory, white noise should not be a problem at all for your model. Problem is that this noise becomes a problem when you need exact measurements, right? Because noisy measurements are by definition not exact. But luckily, biomedicine is not exact, right? Think about gene expression measurements or what have you, right? Don't tell me those are exact, they're not. By no means are those measurements exact. So forget about noise, not a problem for us. Distribution shifts, those are actually more interesting. Also, if you think about genomics, for instance, so the concept is basically that your real-world data set differs somehow systematically from your training data distribution. And if you think about genomics, most of the stuff we know in genomics is actually based on white males of European descent. Just because all the GER studies that are out there are done for white males of European descent. Damn. What are we going to do with the black African woman? It's not in the reference data. We will have a hard time to do anything meaningful with that. Right? You have completely different LD structures in African or Asian genomes than you have in European or American genomes. So all of these things are not accounted for or have not been accounted for a very long time. So this is actually really a problem for us. What you can do, of course, ideally is train a model on diverse domains. So for God's sake, just start including black African women in your GER studies, right? Get data from other domains. Make sure the model sees what's out there in the world and not just what's in the database in your hospital. If you can do this, problem solved. Unfortunately, it's, well, again, at the point of sample collection and so on, right? It's not that easy. Or other examples of distribution shifts, if you're into images, right? You can have cross-site shifts. You can have learned something on CT scans, which you then want to apply to MRIs, where you have a distribution shift. You can have time series data where you have distribution shifts across time, or you can have distribution shifts across protocols, so different vendors of machines that you're using, right? Whether your machine is from Siemens or from, I don't know what other companies build these machines, but there are some. So all of these are distribution shifts that we somehow need to take care of. If you have not the possibility to collect data from all these other domains, then you probably need to go into things like batch effect correction, transfer learning, or domain adaptation workflows, or data augmentations for images, right? So we don't have the time to go into this, although there's no exclamation mark here, so it's not too hard. But data augmentation for images is quite easy, right? You just like add certain levels of contrasts or white balances or sharpen or de-sharpen the image. and by that can simulate kind of distribution shifts in your images relatively straightforwardly and without too many overhead. Now something that's not that relevant in medicine, but is still something that you should keep in mind if you design AIs, adversarial attacks. So if somebody actually on purpose wants to fool your AI model. For instance, here you have predictions by deep neural networks, and this is clearly a robin, this is clearly a cheetah, here you clearly see a peacock, and so on, right? So the models are really certain about these predictions. Or this is clearly a starfish. Who would have thought, right? I mean, this arguably looks somewhat like a baseball because of this red suing, maybe. Or somewhat an electric guitar, right? But I mean, this is like, why? Now we could use Lime to kind of highlight some pixels here, but that would arguably not help very much. And you would say, okay, but why do I care? I can just have fun with neural networks, right? Well, what you can do is if you have a network that predicts a duck and you add this, it suddenly predicts a hermit crab. Again, this is fun, right? You can just play around with this. But at some point, fun stops, right? If you have self-driving cars that want to recognize traffic signs and somebody really hates you and then changes a stop sign like this is bad. So it's not very medical. I mean, in theory, somebody could change your X-ray to change the diagnosis or something, right? But I don't think somebody would actually do this, whereas this, I think, is actually a real threat if you think about self-driving cars and whatnot. So keep this in mind. If you do machine learning, that you kind of, if you do it in a domain where this is relevant, that you try to prepare your model for these adversarial attacks, where somebody actually on purpose wants to change the predictions or the behavior of your model. There's adversarial training and robust optimization techniques for this out there that you probably find when you Googled it, but it's a bit outside the scope of this lecture. Some of the stuff I stole from other courses. And in conclusion, in a medical context, I would argue that prediction should be meaningful, right? So we should make sure that our model actually learns something meaningful. They should be interpretable or explainable, and they should be robust. Like batch effects are a huge topic in biomedical research, right? Network-based approaches in a sense of molecular interaction networks can help a lot with this, as we will see later. For now, just please keep in mind, at the very least, if you develop some machine learning model, perform cross-validation and permutation tests. I don't want to see any ML out there without permutation tests, please. And additionally, try to make your model interpretable and robust, for instance, by using SHAP or some data augmentation techniques. And with that, thank you very much.
Now we have time for a question or two from the public. Does anyone have a question that would like to make?
Hello, great talk, thank you. Why isn't the permutation test a test for robustness?
Sorry?
Why isn't the permutation test a test for robustness in a model?
You could probably devise a permutation test for robustness by permuting according to specific distributions. So the issue with permutation tests usually is that you completely break any connection between features and outcome, right? So there's not just a distribution shift, but you basically get rid of the whole distribution if you want. You could, but this probably becomes a bit tough in terms of sampling and so on. You could try to emulate a certain distribution shift in a permutation test to assess robustness. But this would be like a more handcrafted test and not an off-the-shelf permutation test.
Thank you so much for your answer, Doctor. Is there another question for us to go ahead? Okay, we will begin the next lecture in a few minutes, so I suggest you guys remain seated we just need to take a few minutes to change the opponents, and that's it. Thank you for your attention. Thank you, Doctor, for your great lecture. Can we give an applause to Dr. Tim Kacprowski?